We have been looking at the principal component and its nuances in the last few lectures. We saw what principal components are, how we can find them through the eigenvectors, and how the eigenvalues can be used to find the variances of the principal components. What we have not seen, however, is how to compute the principal components given a set of data. So, what we will do in today's lecture would be to look at principal components from a sample point of view. So, given a data set, how do you compute these principal components and what their implications are? This is what we will start with, and then we will look at how these sample principal components are related to the population principal components that we have already discussed. So, are these two related, or how closely do they match? So, some of the large sample theories of this we will be looking at also. And finally, what we will look at is an example. So, given a data set, how do you calculate the principal components and how do you understand the implications of this principal components, and maybe finally how you really use them in further studies. So, suppose we do the principal component, and these are the results that we get. So, we see that the eigenvalues of the correlation matrix obtained from this data. So, the first thing that we do, of course, is we compute the correlation matrix for this 8 variables. So, it is a 8 by 8 correlation matrix. Find the eigenvalues. So, there will be 8 eigenvalues for this, and these come out to be in order. The largest is 7.0002, the next is 0.6508, and it keeps decreasing to the last one, which is 0.0149. Of course, the sum of the eigenvalues should be what? It should equal to the number of variables. Mind you, we are doing a orthogonal transformation here, and it comes out to be 8. Now, let us look at the proportion of variability explained by each of this. Remember again that the eigenvalues give such the variability for each of the principal components. So, total is 8. The first principal components lead to an eigenvalue of 7. So, it has a variability of 7, and hence the proportion is 0.875, which comes from 7 by 8. The next one accounts for about 0.081 variability. Let us look at the third column. The third column shows us that the first two accounts for about 95% of the variability. It is the cumulation of the first two. And when we come to the third one, which has a very small contribution now, 0.012, the total comes up only to 96 or almost close to 97% of the variability. So, you see, we have covered almost the whole of the variability if you look at the first 2 or 3 principal components. The first two covers up 96% almost, and then second one covers up to the third one covers up 97%. So, we need not go any further, and we can work with this smaller number of principal components. So, what has this done? It has reduced 8 variables into only 2 or 3 principal components, which cater to the maximum variability that was there originally in the data, and the remaining principal components we can discard because they account for very little of the remaining variability. But how do you choose the number of whether it should be 2 or 3? Now, as before, we consider a linear combination of the x, that is, we have y is equal to a prime x, which is basically summation of k equal to 1 to n a k x k. So, x k's are the elements of x, and as you remember, we will be looking at this linear combination y. Now, we can do this for each individual. So, we can write this as y I, which is equal to a prime x I. In this case, x I stands for the ith individual with k characteristics, and if we compute the mean, then we have the sample mean for y as y bar, which is equal to a prime x bar. What would be the sample covariance matrix? It is given by variance of y, which is a prime S A. S, remember, is the variance covariance matrix of the x's. As before, we apply the principal component technique here. What is that? We will be selecting A in such a fashion such that the variance of y is maximized for the first principal component, and then the successive variances would again be maximized, but the coefficient should be orthogonal to all the previous principal components that you have got. So, the jth principal component would be given by yj hat is equal to pj hat prime x. What is pj hat here? Now, let us go back and look at S. Now, S is a positive definite matrix, and let lambda 1 hat, lambda 2 hat, lambda m hat be the eigenvalues of S. And without loss of generality, let us assume that they are ordered, in the sense that lambda 1 hat is greater than or equal to lambda 2 hat, etc., which is greater than or equal to lambda m hat. So, we have m eigenvalues which are ordered. Some of them may be equal, or else all of them may be distinct. It does not matter. But let P1, P2, Pm hat be the corresponding eigenvectors. So, P1 hat corresponds to lambda 1 hat, etc. So, these eigenvectors are, as before, used as the coefficients of the x's in forming the principal components. The first principal component is given by y1 hat, which is P1 hat prime x. The second by y2 hat, which is P2 prime hat x, etc. So, we can form the principal components as before by taking the linear combination of x's combined through the jth eigenvector to obtain the jth principal component. So, these are results we have done for the population case, and these results hold similarly for the samples as well. So, in this case the results are almost similar. So, I am not going to prove these results, and we can show that this first principal component would be maximizing A prime S A by A prime A, and the technique would be exactly similar. And once we have computed all the principal components this way, we can also show that the sample variances of this principal components, that is yj hats, would be lambda j hat, and this is true for all k equal to or j equal to 1 to m. And remember, as before, we would be selecting this a's for each of the principal components such that it's orthogonal to the previous ones. So, the sample covariances between two principal components, that is yj hat and yk hat, would be equal to 0 for all j not equal to k. As before, the total sample variance would be given by the sum of the eigenvalues. So, in this case, the total variance is equal to summation j equal to 1 to m lambda j hat square. And obviously, the proportion of variability explained by the first principal component would be lambda 1 hat divided by this sum of lambda j hat squares. Okay. So, the sum of the lambda j hats would be acting as the total sum of squares, and we can look at the individual lambdas, and the ratio would give us for each of the principal components the amount of variability that particular component explains. So, the first k principal components will explain lambda 1 hat plus lambda 2 hat, etc., up to lambda k hat out of the total of lambda 1 hat to lambda m hat. Obviously, k is less than or equal to m, and as before, we would be choosing the number of principal components based on how much of the proportion is explained by the first k of the principal components. Generally, we can draw a scree plot which would be plotting this proportions against the corresponding lambdas. Select the number of principal components to be included based on the position of the elbow. So, this is exactly what we had been doing before, but in that case it was for the population. In this case, we are doing it for the sample. One other thing that we can do here is that once we have got the principal components and we have decided on the number of principal components that we want to work with, maybe the first 2, maybe the first 3, we can for each individual compute their principal component values. So, suppose for the ith individual we have the vector xi, then his first principal component value would be given by y1 hat is equal to p1 hat xi. So, that is his first principal component score. His second principal component score would be y2 hat is equal to p2 hat xi, and similarly I can maybe get the third one or the fourth one depending on how many I want to keep. So, instead of looking at his m dimensional vector, I can now look at this individual's principal component values. So, that will be also a vector, but a vector of a much smaller dimension. And in further studies, we can think of working with the principal component scores rather than with the original x's. That is one of the major reasons why we do principal component. We have reduced an individual's m dimensional score vector into a smaller, say 3-4 dimensional principal component score vector, and then work with this principal component, because this would be actually capturing a large amount of the variability of the original data and would have a smaller number of variables to look at and hence easier to handle. So, this is how we can use the principal component from a given data set. Now, let us see how these principal components that we have obtained from the samples, how these are related to the actual population values. And of course, what we will be discussing now would be basically large sample properties, because there are no such small sample results relating the two sets of principal components, one obtained from the sample and the other obtained from the population. So, let us assume x1 are a sample from a normal population with sigma having distinct eigenvalues lambda 1 greater than lambda 2 greater than lambda m, and of course, all of them are positive. Then let us define capital delta as a matrix which is diagonal by nature and which has the lambda j's on its diagonal. So, it is diag lambda 1 to lambda m. Again, lambda is a vector which is composed of this same eigenvalues lambda 1 to lambda m. So, the distinction only is that capital lambda is a matrix where the eigenvalues are on the diagonals, and the other lambda basically is a vector with the same eigenvalues. Okay. Now, we can show that root over n lambda hat minus lambda is asymptotically normal with mean 0 and variance twice capital lambda square. So, what does this mean? It means that if we have a very large sample, then the sample eigenvalues tends to the normal distribution and it has population eigenvalues as its mean, and the variance turns out to be 2 by n lambda square, which is capital lambda square. So, if you look at them individually, what it tells us is that each lambda I hat, if you look at the jth principal component, each lambda j hat is approximately a normal distribution with mean lambda j and variance twice lambda j square by n. Remember, capital lambda is diagonal, therefore, these are uncorrelated with each other, and hence we just need to look at the variances. So, it is easy to get this results for each of the individual lambda j's. Correspondingly, we also have a result for the eigenvectors. Look at the jth eigenvector, then we can show that root over n pj hat minus pj is asymptotically normal with mean vector 0 and dispersion matrix ej, where ej has a slightly complicated form. It is given by lambda j summation k equal to 1 to m, but k is not equal to j, and it sums up lambda k by lambda k minus lambda j square into pk prime. And more importantly, the lambda j's are distributed independently of the elements of pj hat. So, lambda j hats and pj's are independent asymptotically. What does the results lead us to? Primarily, we can show that in this case, firstly, if you look at the coefficients for the sample principal components, these were given by Pj hat, and for the population it was given by Pj. So basically this would be, one would be tending to the other for large samples. So coefficients or the combining weights basically for the sample tends to that of the population. The other thing is, if you look at the variances which are given by the lambda j's, these variances for the samples would be tending to the variances for the population, and they would have a normal distribution again. Now this results also allows us to form confidence intervals for the lambda i's. So notice that lambda j hat is normal with mean lambda j and variance twice lambda j square by n. Therefore, probability of lambda j hat minus lambda j modulus of this is less than equal to tau alpha by 2 lambda j into root over 2 by n. This is equal to 1 minus alpha. Now what does this imply? It implies that we can form confidence intervals for the lambda i's, and then after a little algebra what we can find is that lambda I lies between the two limits lambda I hat by 1 plus tau alpha by 2 root over 2 by n and lambda I hat divided by 1 minus tau alpha by 2 n. So this gives us the two confidence limits for lambda j. So from this results we can see that the sample eigenvalues and the eigenvectors tends to the population eigenvalues and the eigenvectors for sufficiently large n, and hence we can say that the same happens for the principal components. So if you have sufficiently large n, then you can expect that the sample values would reflect very closely the population values. Consider the data on different type of track events. We take 8 different track events, the 100 meters, 200 meters, 400 meters, 800 meters, and then the longer ones 1500 meters, 5000 meters, 10,000 meters and the marathon. And we have the records for the different countries over a number of years. So we have a large number of countries that we have included here, and these are the track records. So instead of looking at this 8 variables, can we summarize this result and look at a number of variables to say which country does well in which sort of event, etc.? Yes, if we want to do that, that would be a question of dimension reduction, and we can apply the principal component method here. So suppose we do the principal component, and these are the results that we get. So we see that the eigenvalues of the correlation matrix obtained from this data. So the first thing that we do, of course, is we compute the correlation matrix for this 8 variables. So it's a 8 by 8 correlation matrix. Find the eigenvalues. So there will be 8 eigenvalues for this, and these come out to be in order. The largest is 7.0002, the next is 0.6508, and it keeps decreasing to the last one, which is 0.0149. Of course, the sum of the eigenvalues should be what? It should equal to the number of variables. Mind you, we are doing a orthogonal transformation here, and it comes out to be 8. Now let us look at the proportion of variability explained by each of this. Remember again that the eigenvalues give such the variability for each of the principal components. So total is 8. The first principal components lead to an eigenvalue of 7. So it has a variability of 7, and hence the proportion is 0.875, which comes from 7 by 8. The next one accounts for about 0.081 variability. Let us look at the third column. The third column shows us that the first two, it accounts for about 95% of the variability. It's the accumulation of the first two. And when we come to the third one, which has a very small contribution now, 0.012, the total comes up only to 96 or almost close to 97% of the variability. So you see, we have covered almost the whole of the variability. If you look at the first 2 or 3 principal components. The first two covers up 96% almost, and then second one covers up to the third one covers up 97%. So, we need not go any further, and we can work with this smaller number of principal components. So, what has this done? It has reduced 8 variables into only 2 or 3 principal components, which cater to the maximum variability that was there originally in the data. And the remaining principal components we can discard, because they account for very little of the remaining variability. But how do you choose the number of, whether it should be 2 or 3? Let us look at the scree plot, and the scree plot shows that there is a very distinct elbow at 2. After that, it becomes almost flat. So, going from 2 to 3, 3 to 4 actually does not incorporate too much of variability, and we are just including more and more principal components. So, given the scree plot, it is reasonable to take the first two only as the relevant principal component. And if you do the plot for this, a plot of the first principal component and the second principal component, most of the variability lies along the first principal component. This is more so because you have a very outlying value here on the extreme left. There is less variability in the second component, and if you could have plotted the other components, you would have seen that they would have been more and more clustered together. So, in this case, it is sufficient to work with the first two. Finally, what is the first principal component? Let us look at what the PCs give us. So, PC1, they give you some coefficients here. These coefficients are basically the coefficients of the corresponding variables. So, suppose I name the variables as x1, x2, x8. x1 is 100 meters, x2 is 200 meters, etc. x8 is the marathon. Then the first principal component would be given by minus 0.341 x1, minus 0.346 x2, minus 0.364 x3, etc., minus 0.334 x8. Similarly, the second principal component would be given by 0.46 x1, 0.434 x2, etc., up to minus 0.524 x8. So, these are basically the linear combinations that we can have. We are looking at a sample. So, suppose let us look at the first country here, Argentina. For Argentina, what would be the y1 value? We have the x values here. So, we put the x's in the first equation and compute the y's. We know the coefficients now. So, we can get y1 for the Argentina and again y2 for Argentina using the second equation. So, that would be the principal component scores for Argentina. So, instead of 8 countries, we now have 2 countries. We can do it for all the other countries. We can do it for India also, where y1 would be minus 0.341 into 10.6 minus 0.346 into 21.42 and so on and so forth till minus 0.334 into 131.98. This would give us y1 for India. Similarly, using the second equation, we can get y2 for India as 0.461 or rather 0.460 into 10.6 plus 0.434 into 21.42, etc., up to 0.524 into 131.98. That would be y2 for India. So, this way you can get the principal scores for each of the countries, and instead of using the 8 variables, can do with only 2 principal components. In today's lecture, we discussed sample principal components, that is, principal components computed from a given set of data. We have looked at their relationship with the population principal components, how you can build confidence intervals based on the sample principal components, etc. And finally, we have looked at an application where we can use principal components and how we can interpret these results. We have over the last 3 plus this lecture looked at principal components in general. So, to sum it up, we have been looking at a method of reduction of dimension, and we have stated that principal component is one of the major ways of doing it. And what you can do here is that you can summarize the information contained in a large number of variables in a few principal components. What is the use of this? First of all, it is easier to look at a smaller number of variables than at a larger number of variables. The other reasons for computing principal components are its applications in different areas. For example, in regression. So, we can use, instead of the whole set of regressors, we can use a smaller set of principal components actually obtained from this larger set of regressors and do the regression on the basis of the principal components. So, there are several uses that we can put this into. So, we have done a comprehensive way of shortening or reducing the dimension of a data in terms of the number of variables included.